Hello everyone. Today in our power system subject, we are going to discuss or to talk about power transformers. Before we go into power transformers, I would like to give you a quick brief about power network. What's a power system? Power system is made of three main elements: generation, transmission, and the load. So you need a part to generate the power, another part to transmit this power to the load, and the third part is the load itself to take this. Missing one element, we will not have a complete power network. So we will generate the power, then we will transmit this power to a transmission line. Now, for us to transmit the power, we have to take into consideration two main elements from electrical point of view. Element number one is power losses along this transmission line. And the power losses is related to the resistance of the transmission line. Number two is the voltage drop along the transmission line. So we have to take into consideration two main elements. Element number one, we have to take into consideration I squared R, and we have to take into consideration I multiplied by Z. This is Z of the transmission line. Now, taking these two parts into considerations will allow us to design an economical power system. So, for my best interest, I need to lower my current. If I lower my current, I lower the losses and I lower the voltage drop. How do I do this? That's where the magical transformer comes in. Transformer will allow me to step up and down the voltage, step up or down the current. So, in order for me to reduce this, what I do is, I will install a transformer. I will take the voltage up. Remember, the power will not change, which reflect into current going down. By doing so, I reduce the current, which is I reduced I squared R, I reduced IZ, the voltage drop. And then, after the transmission line, I could have another transformer to go down to another transformer and then goes down to load. So I could have a power stations, have a transformer to step up, transmit the power into a transmission substation. What I have large number of transformers, large number of transmission line, or as they know, feeders, and then I go from the transmission substation to a distribution substation or a zone substation in some countries, and all this will take me to the load. That's what I need to know now. Transformer also played a vital role, a very, very important role in the 1800s when there were, the competition between the AC and DC. In 1885, Mr. William Stanley introduced the first commercially used transformer, which made AC very favorable to everyone and led to the AC push-up. Now, nowadays, the advancement into technology, the advancement into power system, allow us to design a transformer that almost 100% efficient, almost 100% efficient, and have a massive power. The power could be 1300 MVA or up. This massive power allow me to expand my power network to a different dimension. There is, in our chapter, we are going to study two types of transformers. Not two types, two sections. One, we will start with an ideal Then we go into practical. We will study the single phase, the three phase. Then we study single winding, double winding, auto transformers. We will go into multiple cases. Now, let's start with an ideal transformer. What's an ideal transformer? For an ideal transformer, I need to define the boundary of an ideal system. Number one, for an ideal transformer, I have to make sure that the windings has no resistance. That's the assumption. So I don't have I squared R. So number one, for an ideal transformer, I have to take into consideration the windings, number one, the windings has zero resistance. This will give me I squared R is equal 0. That's for an ideal transformer. Great. The second assumption is the permeability of the material must be 0. The core permeability mu, the mu of the core is infinite. Because the core mu is the reluctance of the core, now will become 0. So also I will not have any losses from a reluctance point of view. And number 3, the leakage flux. Number 3, I have no leakage flux. No leakage flux, that means the flux generated, the phi generated, the flux generated at the primary side, it's all of it goes to the secondary side and also get back into electricity, no losses whatsoever. That's the third one. The fourth one, which is most important, I have no core losses. These four conditions define, the four conditions that define an ideal transformer. Let's just sketch an ideal transformer and you will see. Now I have, this is a single phase transformer. I have a windings on the primary side, I have a windings on the secondary side. I have V primary, one I call it I primary. This has N primary, number of winding N. On the secondary, I have number secondary, I have a V secondary, and I have I secondary. Under ideal condition, I have resistance is 0 of these windings. Also, I have, this is my flux. This is the direction of my flux. Also, I have this, the material that made of this ferro material is made of mu of C is infinite. Which means the magnetic circuit representation of this magnetic circuit, the reluctance will be 0. And the entire flux, I have no leakage flux. I have no leakage. No leakage. All of it will goes from here, reach at this point. Therefore, I'll eliminate all kind of losses. All type of losses. Now, I can represent this transformer by this. V primary, I primary, N primary, N secondary, I secondary, V secondary. I can represent the ideal transformer with this representations. I hope that's clear. Now, let's go back to the next stage in regard to our calculations. What can we cover from our calculations? Now, when I come to an ideal transformer, I want to recall back what we studied in physics. I want to go back to Ampere's law and Faraday law. Let's start with Ampere law. What does Ampere law state? It's the empirical integration of H related to the magnetic field will equal to the I enclosed into a surface. Now, I'll have H in respect of the length, will be equal to I enclosed. That's Ampere law, isn't it? Remember from physics 2, enclosed. Now, this Ampere's law. When I come to our magnetic circuit, I will have HC for the core, LC for the core should equal to I primary, N primary minus I secondary, N secondary. The LC is the length of our transformer. H of the core is equal to, this is the primary data and the secondary data. What's a magnetic field density B? If I take into consideration B of the core, what's the B of the core? B of the core, it's equal to mu of the core, permeability of the core, times HC of the core. What's the flux of the core? It's equal to B of the core multiplied by the cross-section area of the core. Multiplied by the cross-section area of the actual core. Now, if I rearrange this network a little bit, all I have to do is take H of C, H of the core, it's equal to B of the core divided by mu C. I'll take this, put it back into here, and this will give me B divided by mu C L core, it's equal to IP NP minus IS NS. All I have to do now is replace this will give us the total system. The total system will give us phi of the core, LC, L of the core, divided by mu of the core, cross-section area of the core, it's equal to I primary under ideal system. This is infinite, so therefore that will be 0. Therefore, I primary and primary, it's equal to I secondary and secondary. And this is the relationship of a transformer. I have I primary and primary, it's equal to I secondary and secondary. And if I go ahead now and I use Faraday law in a similar way, remember, our scope it's not to go and verify the magnetic circuit of a transformer. This magnetic circuit already been covered under previous chapters, previous courses, prerequisite. So if I apply Faraday law, which is related to the induced voltage is a d of the flux, that d phi of t over dt, it will give me this relationship, which is V primary over N primary is equal to V secondary over N secondary. Based on Faraday law and Ampere law, I generate these two, along with the magnetic circuit, I generate these two relationship between the primary voltage, the secondary voltage, primary current, the secondary current in respect of the number of turn of a transformer. Now, one element, Np over Ns, is known as A, which is now V primary over V secondary is equal A. This, the relationship between primary current, secondary current, primary voltage, secondary voltage in respect of our number of turn of a transformer. After we study this, we need to also the power. We usually, whenever we study an electric circuit, we have interest in current, voltage, power, impedance, these elements. For a transformer, an ideal transformer, the input complex power, it's equal to output complex power. That's very, very important for us. The complex power entering the primary side equal the complex power leaving the secondary winding. That's for an ideal transformer where I have no losses. It's very important to know S1 it's equal S2 for ideal transformer. For an ideal transformer, the complex power of the entering is equal to complex power exiting. One more element, one more relationship I need to establish for an ideal transformer is the impedance relation between the primary and secondary. Pay attention to this. Let's assume I have a single phase transformer. That's an ideal transformer, single phase. This transformer is supplying a load of Z2. That's V secondary, I secondary, V primary, I primary, N primary, N secondary. If I apply Ohm's law on the secondary side, I have Z2 it's equal to Vs over Is. Now, I need to look from the source. I am the source of power going through a transformer to a load. I need to find the relationship. What does the actual source see irrespective of the impedance, the load impedance or Z2? Okay, for this current to drive through, for this current, must be a Z, an impedance that drives this current from this voltage. I always have V it's equal IR, V it's equal IZ. I need to find the Z, that the voltage, the source voltage C, and to allow for this current to go through. I want to call it Z2 dash. Z2 dash will be equal to V primary over I primary. Now, what I have to do is, I have to take this and I will say Z2 dash. What's V primary? What's a V primary? It's equal A V secondary. it's equal to A V secondary divided by, what's I primary? I primary, it's equal to I secondary over A. If you look at it from this point of view, I have I primary, it's equal to I secondary multiplied by NS over NP. Check it. Check this. Is that clear? Okay, beautiful. Now, this will give me A squared Vs over Is, which gives me A squared Z2. So, from this scenario, I can clearly see that the impedance seen from the source on the primary side of the transformer, it's A squared, which is NP over NS squared, times the connected load. So now I can put the relationship Z2 dash, it's equal to A squared Z2. Let's put it on this side of this table to cover all the relationship. Z2 dash Z2 dash is the impedance seen from the primary for the load. I hope that's clear. Now, let us practice an example. Let's take a few seconds, take a deep breath, and let's do an example. For our example, we are going to consider 20 single phase, 20 kVA power transformer, 480 to 120 volt system. This transformer will supply the transformer will supply a load. The load is 15 kVA. The load is 15 kVA. The load is 15 kVA. Lagging of 0.8 power factor, and V load, it's equal to 118 volt. This is what's being given. The first question is, I need to find the voltage on the primary side. I need to find the voltage on the primary side. Look. This is the load. I have 15 kVA, 0.8 lagging power factor, V load, which is V load, it's equal to 118 volts. Beautiful. This transformer is 480 to 120 volt, which means this will give me the relationship of A between N primary and N secondary. Pay attention. I have V primary, it's equal to N primary over N secondary times V secondary. The relation of A, which is equal to A times V secondary. In our case, it's equal to 480 divided by 120 multiplied by 118. This will give me the V primary, and that one will give me 127.12, 472 volt. This will give me 472 volt. So in here now I have V primary, it's equal to 472 volt. Remember, these are the rated value of the transformer. This is if you have 480, it will give you 120. That's why I know what's A. A is V primary or V secondary. Now, if the voltage changes at the primary or the secondary, A will never change because the number of turn, I did not touch them. I did not change the number of turn. 20 kVA is the rated of the transformer, so can give you up to 20 kVA. This system has a 15 kVA, which is great. There's no issue. I have no problem in regard to this. So the first question, calculate the primary voltage across the primary winding, which is we've done. The second one is the load impedance. I need to calculate the load impedance on the secondary side. I need to find Z2. Beautiful. Great. All I have to do now is use circuit analysis. How I do this? For the primary side, for the secondary side, I have S2, it's equal to 15 kVA. I have V secondary, it's equal to 118, and I have the angle of this one is inverse cosine of 0.8. I apply S2, it's equal to V secondary, I secondary, so therefore I calculate I secondary will be equal to 15 10 to the 3 divided by 118. The angle of minus, see the minus? Because of the star, of the conjugate, minus cosine inverse of 0.8. So I secondary, the answer of I secondary will be 127.12 angle minus 36 degrees. Z2 will be equal to V secondary divided by I secondary, and for Z will be 0.928 angle of 36 degrees. Is that clear? Now, the third question is calculate the impedance seen from the primary. The impedance seen from the primary, all I have to do is I apply the equation that I learned, which is Z2 dash, it's equal to A squared, Z2, which is equal to 480 divided by 120 squared, multiplied by 0.928 angle 36 degrees, and the answer will be 14.85 angle 36 degrees. This is in ohm. Remember, don't forget the actual unit in all your calculations. Is that clear? The last question that can be asked is to calculate the power at the primary side. The power at the primary side, because it's an ideal transformer, it's equal to the power on the secondary side, which is equal to 15 kVA, 0.8 lagging power factor. Is that clear? Does that explain the entire concept behind an ideal transformer? So let's recap. Transformer, it's a very, very important topic, very important element when it comes to our power network, power system. That's number one. Number two is an ideal transformer is defined by 4 categories, 4 elements. Number one, I have 0 resistance for the primary and secondary winding, so I eliminated I0 squared. Number 2 is mu of the core. The permeability of the core is infinite. This will give me a reluctance from a magnetic circuit to be 0. I have no leakage flux the flux that goes through from the from the primary go to secondary, and I have no core losses. After I determine my ideal condition, if my transformer sit within my ideal conditions, I can go ahead and apply all the theory that we studied today. I hope that was clear, and now we'll run a session for questions.